In this section, we're going to show you how to estimate the survival curve from a sample of data. It's something called the Kaplan-Meier approach. This is a very famous approach. And Kaplan and Meier were two statisticians who invented this in the 1950s. And Paul Meier was actually on the faculty at Johns Hopkins for a fair amount of time. What they considered was they wanted to estimate this survival curve based on a sample of data using full information on some subjects and censored information on others. What they wanted to estimate as a function of time was the proportion remaining event-free or surviving to at least time t or beyond. So S of 60, for example, will be the person who has still not had the event by 60 days. This curve always equals 1 or 100% at time 0 by definition. The only way we can do these studies looking at time to event is start with a bunch of people who have not yet had the event. So they all have to be event-free at time 0. So S of 0 or S of t equal to 0 is always 1. The curve always starts at 1 at time 0. All subjects are event-free at the beginning of the study. And from there on in, it can only remain at the same value or decrease as time progresses. So it can only stay at 1 or go lower. If all the subjects do not experience the event by the end of the study window, if the largest times we have are censoring times, the curve may never reach 0. And we'll consider an example of that among our examples. We can estimate this curve from a sample of data, and the statistic we have to estimate it is sometimes called S of t hat. And the hat just goes on top to indicate we're dealing with a sample estimate. There are two well-known approaches to doing this. One is the life table method. We're not going to consider that in this course, but you may have seen it in another course like epidemiology or demography, where we consider events occurring in time intervals, but we don't recognize the exact times that they occur. The Kaplan-Meier is like an expansion of the life table method that looks at ungrouped data and can be done in small or large samples. So let's look at an example here. Here's the time from primary AIDS diagnosis for a sample of 12 hemophiliac patients under 40 at the time of HIV seroconversion. This is the time to death in months from the primary AIDS diagnosis. So here we call them the times, event times, but some of them are censoring because they indicated with the plus to the right of that. So in this sample, the first subject in this listing here died 2 months after the primary diagnosis of AIDS. The second subject was censored at 3 months, etc. So here's how we're going to go ahead and summarize this data using all the information we can from the censored events, but recognizing that they're only partial pieces of information. So we're going to start the clock at 0, time of AIDS diagnosis, and by convention our curve will be 1. S of 0 will be 1. S hat of 0 will be 1 to start. After starting at time 0, the curve can be estimated only at each event time afterwards, but not at the censoring time. So this curve is only going to go down at event times, and will otherwise remain at a constant value until the next event hits. So this curve will stay at 1. The estimated proportion remaining event-free will stay at 1 through times up until the first event time, where then it will drop. And what we do, this is kind of interesting. It involves two pieces of information to estimate S hat of t. And there's a lot of notation here. Don't worry so much about the notation, but just think about the idea behind it. What we have to do at each time point, each event time, is track how many people were around right before that time, and ergo were at risk in our sample to have the event at the time. And then we also have to keep track of how many of those who were around actually did have the event at that time. And the way we estimate the cumulative proportion of the original sample who remained event-free at a given time is we do it piecewise. We first look at the proportion of the original sample making it up to that time. That's the proportion of people who were around right before that time from the original sample who could have the event at the time we're looking at. And then we multiply that by the proportion who were actually around at that time who make it beyond that time. This is two pieces of information go into this. What proportion of the original sample is around right before that time? And of that group, what proportion make it beyond that time. And those two pieces of information put together give us an estimated proportion of the original sample who makes it beyond that next event time. Let me just show you an example here. I might make it more real. So in this example here with death after AIDS diagnosis in the hemophiliacs when AIDS was first becoming an issue in the 80s, what we'll do is we'll start. You have to order the times, event and censoring times in order of magnitude to start. These were already ordered. And we actually start, the curve starts at 1, so S hat of 0 is 1, and it stays at 1 until we hit the first event time. So S hat of 0.5 is 1, S hat of 1 month is 1. Nothing happens until the second month where we see our first event. And so here's how we're going to do it. S hat of 2, well, 100% of the sample was around at that point to have the event. And of that 100%, there were 12 people around to have the event. Of those 12 people, 1 person died and the other 11 did not. So of those 12 who were around to have the event, 11 did not, which turns out to be 92%. So 92% of the persons who could have the event did not and survived beyond time 2. And what proportion of the original sample was around right before time 2? Well, it was the 100% we started with. So 92% of the 100% who could have had the event did not at time 2, which means 92% of the original sample survived beyond time 2. We can now estimate S of t at each subsequent event time. So we're going to skip over that 3 who was censored and jump right to the 6s. So we see 2 events at time 6. So let's piece this together. At time 6, how many people were still around? Well, we lost 1 person at time 2 to death, and we lost 1 person at time 3 to follow-up, lost to follow-up. So of the original 12, only 10 were still around to have the event. Of those 10, 2 people had died at 6 months after their AIDS diagnosis. So 8 of the 10 people who could have had the event at time 6 did not. Okay, so 80% of the people who could have had the event at time 6 did not and survived beyond time 6. And what percentage of the original sample do we estimate was still around going into time 6? What was the 92% who made it beyond the previous event time, time 2? So putting this all together, 80% of the 92% of the original sample who were around to have the event did not. So cumulatively, 74% of the original sample, we estimate, made it beyond time 6 without having the event. So how does censoring come into play here? Well, let's take a look at another example of the curve. We're going to skip over that at 7, because that's a censored observation, and jump to time 10, which is where we observe the next event. So at this point, there were 7 people still around who had made it right before time 10, who could have had the event at time 10. Of those 7, only 1 of the people did. So 6 of the 7 people who could have had the event at time 10 did not and made it beyond time 10. So what proportion of the original sample did we estimate was still around right before we got to time 10? Well, it was the 74% we estimated who made it beyond time 6. So 6 out of 7 of the 74% who could have had the event at time 10 did not. And when we put that together, that 86%, which is 6 out of 7, 86% of the 74% of the original sample who could have had the event at time 10 did not, which translates into 64% of the original sample surviving or remaining death-free beyond 10 months. And we could go through all this by hand, but I'll let you look at this table here, and maybe you want to try and verify the other numbers to get some handle on this methodology. But you see in this table, we only actually change the function at event times. So in that column T there is only the event times are listed. And you can see this goes all the way down to 0 because the largest time in our set was not a censoring time, it was an event time. So at that point, nobody had remained of those who could have at time 32. So let me ask you this before we go on. How did we use the information about censoring individuals in developing these estimates here? We never actually changed the curve at one of the censoring times, but how did we actually incorporate the information from those who were censored? Well, you notice that anybody who was censored played a role in defining our number of people at risk at any given time up until the point they were censored. So they actually informed us about the body of persons at risk until they dropped out of the study, until we could no longer track them. So we knew, for example, the person who was censored at 3 months, we knew that he was eligible to have the event at 2 months and did not. We don't know what happened to him after 3 months, but we knew he was around to have the event at 2 months and did not. So he constituted part of the body of people at risk at 2 months. And then we lost him at 3 months, and he never entered our calculations again. But he was around there. So the censored individuals inform us about who's at risk up until the point they're censored. And if you ignored the censored individuals, if you went back and just dropped them out of the process, you would see the curve dropping a lot faster, and we'd be, again, underestimating characteristics of the survival function by having it drop faster. We'd miss part of the story if we ignored the censored individuals. So that they provide an important function for us. Well, of course, this can get cumbersome to look at in tabular form. We only had 12 events or censoring times here, but if we had a larger sample, then summarizing this in tabular form may not convey the story all as well as a picture. So we can, of course, turn this into a graph where we plot on our horizontal axis the time and on our vertical axis S of t, and we can connect them as a curve. And what it looks like is actually what's called a step function, a curve with steps in it, because this thing only jumps, changes shape at each observed event time, and nothing is assumed about the shape between each observed event time. So we keep the estimate constant until we observe another event. For our hemophiliac HIV, AIDS, and death example, here's the Kaplan-Meier estimate presented graphically. And you can see it starts off at 100% up until time 2, where it drops to 92% and then keeps going, as we discussed in that tabular format. We can use this data, this summary statistic, to estimate single number summary statistics like the median time remaining event-free. So the conventional estimate, for example, of the median time remaining event-free, the median survival time, as it's sometimes called, is take the first time point where the estimated S hat of t is less than or equal to 50%. The proportion remaining event-free is 50% or less. A lot of times you won't actually hit 50% exactly, especially in smaller data sets. So the convention is to take the time where we hit 50% exactly, and if not, the first time below 50%. So in this situation here, the estimated median is 16 months, because that's where the first point where the curve drops below 50% to 39% at 16 months. So by convention, the estimated median survival time here is 16 months. Let's look at another example. When time in days to resuming smoking in the first month following completion of 5 one-hour group coaching sessions on cigarette smoking cessation. So we have 10 subjects here. What they do is they receive 5 one-hour sessions on smoking cessation. These are people who quit. Some people were not eligible to be part of the study because even after the 5 sessions, they did not quit. So we started with a group of 10 subjects who had quit. We followed them until they either started smoking again, dropped out, or the end of that 1 month period. And so you can see we have some observed relapses to smoking and some censored times. And we want to summarize this. Well, let's first order the times from lowest to largest by order of magnitude, and then start estimating the survival curve, the time to event curve, using the Kaplan-Meier method. So, of course, the first event comes in at 1 day. Somebody made it 1 day and started smoking again. So our S hat of 1 would be, how many people were around right before day 1? Well, all 10 of the people we started with, right? Only 1 of them started smoking again on day 1. So 9 of the 10 who could have started smoking on day 1 did not. So they made it beyond day 1 without smoking. 9 out of 10 is 90%. So 90% of the persons who could have started smoking again did not on day 1. Made it beyond day 1. And what percentage of the original sample was around to start smoking again? Well, it was 100%, because this is the first event we observed. So the cumulative percentage, the proportion of the original sample that made it beyond day 1 without starting smoking again, was 90% of the 100% of the original sample who was around to start smoking again. We'll skip over the person who we lost contact with after day 3. They were censored, but they did inform us about those who were at risk to start smoking on day 1. But now they're no longer part of our story, and we'll estimate the next change of the curve at day 5. So now, how many people were still around right before day 5? Well, we lost one person at day 1 because they resumed smoking, another person at day 3 because they were censored. So now we have 8 people left to fall victims to smoking again at day 5. Only one of those 8 did, so 7 of the 8 who could have did not and made it smoke-free beyond day 5. So 7 of the 8 of the persons who were around right before day 5 to start smoking again did not. 7 out of 8 is 88%. And what proportion of the original sample we started with was around right before day 5? What was our estimate based on the proportion who made it beyond the previous event time, the 90%? So 88% of the 90% who could have had the event did not, which translates into 79% of the original sample remaining cigarette smoking free beyond 5 days. And you can flesh this out and do it on your own, and here's what the curve would look like in tabular format. You can see the last 2 values, 30 and 30, are censoring time. So the largest values in our data set time-wise are censoring time. So this curve never makes it to 0, because at the end of the study, we still had people who had not started smoking again when we finished the study. Here's the graphical presentation of the curve. One big assumption about this method that's hard to verify, sometimes more appropriate than not, is the independence of the censoring and survival. The idea is those that the censored at time t have the same prognosis as those not censored at time t. So it means the risk, if you will, of starting smoking again is similar for everyone in the study, regardless of whether they were censored or not at a given time. Some possible violations of this could come into play, or like time to tumor for animals could be related to, their censoring could be related to how sick they are otherwise, and they may drop out because they succumb to some other condition that renders them ineligible for the study, or like an occupational study, like the healthy worker effect is sometimes it's called, is that the longer you go on following people to see if they, for example, develop injuries on the job or come down with sickness, is you start to lose people early on to censoring because they're already more prone to sickness and they're taking time off because of the sickness, so they're censored. So we won't go too much into this in this course. It's really enough material to warrant a whole year of coursework on its own or more, what to do in those situations. But needless to say, we're already seeing that it's relatively complicated to deal with the simple case, and it gets harder from there on in. But I just want to make you aware of that. So what we're going to do in the next section is we're going to see how to actually, we're estimating these survival curves from a single sample, an imperfect, hopefully representative sample from a larger population, but there's still going to be sampling uncertainty with these. So how do we incorporate that into the story? And that's what we're going to do in the next section.